exact solution method by Blasius. We have already some idea about what is boundary layer, the principal mechanism of momentum transfer inside the boundary layer. We also know that what is displacement thickness, what is momentum thickness, why it is difficult to experimentally evaluate the disturbance thickness, and how can we connect the disturbance thickness with the other two thicknesses. The governing equation for flow inside the boundary layer, we have derived that from Navier-Stokes equation, also from continuity equation. We have defined some sort of a stream function which automatically satisfied the continuity equation. So, we have only one equation to solve, which is a PDE, and that is the Navier-Stokes equation for flow inside the boundary layer. We are going to solve this expression, this equation with proper boundary conditions using the method by Blasius. So, for that, first thing is to find out what is similarity parameter. So, similarity parameter should be, let us define it as eta. It should contain both x and y and some other physical properties as well. So, let us see if we write this expression at the edge of the boundary layer. Which term is going to be 0 at the edge of the boundary layer of this expression? The velocity in the x direction would still be there. The velocity may change by a small amount in the x direction. Vy would be non-zero, and we would solve one problem later on to see whether or not Vy is really non-zero at the edge of the boundary layer. This one will have some contribution still there, but Vx will not change with y anymore at the edge of the boundary layer, because when you have reached the outer limit of the boundary layer, Vx will not change with y. So, this term is going to be 0, and this Vx now is going to be equal to u. So, I am going to have another u. This is just an order of magnitude analysis, an approximate analysis at best. I am replacing this by x would be equal to nu, then u by y square, and in that case y is going to be equal to delta. So, a very rough approximation of this equation at the edge of the boundary layer would take this form. Okay. So, Vx equals u and y would become equal to delta. So, what you have here from is delta is nu x by u. Okay. So, whenever you are trying to find a similarity parameter, see if the governing equation can be simplified or can be written in difference form at any of the edges. Here we are using the edge at y equals infinity, which in practical terms is y equal to delta. So, this is some sort of a relation which we are getting, and if we have to find out a dimensionless form of this eta is, which is a similarity parameter, is y by delta. So, this eta is y root over nu x by u. This is the similarity variable, combination variable, because it combines both x and y, as well as some of the physical properties of the system and system parameter, which is or operating variable, which is capital U. So, it contains all the information, and in most of the cases this kind of an approach is sufficient. I am sorry. Okay. Some approach utilizing a combination variable works very well, which happened for the case of Blasius exact solution. So, the next step remains is since we have defined we are going to express everything in dimensionless form. So, a new dimensionless stream function is defined as, it is just a definition, nothing else, and once we do that, then Vx would be del psi del y, and I can write it as del psi del eta into del eta del y, which is this is the expression for Vx in terms of the newly defined stream function and the similarity variable. These are the simple steps which I am sure all of you can follow. And f is a function of eta only. Since f is a function of eta only, then I can replace the partial sign with the normal differential sign. So, I have evaluated what is Vx. Similarly, I have to find out what is Vy, what is del Vx del x, del Vx del y, and del square Vx del y square. So, all these expressions are to be found out separately. Once they are found out, all of them will contain either f and eta and other system properties. Substitute them back into the governing equation. And if your similarity parameter is chosen correctly, all the x and y's from all sides will cancel out. What you will be left with is f and eta. So, basically if you have only f and eta, it is no longer a PDE, it has to be an ODE, since by definition f is a function of eta only. That is the essence of similarity parameter or combination of variables. When everything, all the terms in the governing equation are expressed in terms of f and eta, if your similarity variable is chosen properly, then your final governing equation should not contain any x or y, only f and eta plus operating parameters. For example, U could be there, the thermophysical property, kinematic viscosity could be there. So, all except for that, no other independent variables would be there. I will only write the expression for Vy, which we will probably use later on, which is half this is the expression for Vy, and this is the expression, this one is the expression for Vx. Now, if you can see, though the Vx expression does not contain any x or y, the Vy contains some x. So, the f I have used some stream function psi. The first, yes, this one. This stream function is dimensional. Since I am expressing everything in non-dimensional form, I have to make this dimensionless. A stream function can be made dimensionless if you look at the dimensions, if you divide it by this. It is just a definition, nothing else. And this I am calling as f, and I understand that f has to be a function of eta only. Okay. So, these are the two expressions which I am specifically writing, since we are going to use them later on in our analysis. But one can see, you can see in your text what would be the expressions of the other three. Now, when all of them are put into the equation, all these x will cancel from all sides. What you will be left with is an expression which is 2 this should be the governing equation. Okay. So, it's an ODE, but it's nonlinear, it's third order. Still, it's much better to handle such an equation rather than using an PDE. So, I need three conditions to solve this expression. So, for some value of eta, I have to specify what's going to be the value of f. Now, the choices for eta, what are the choices for eta? If you look at the definition of eta, which maybe I should write here as well, the choices for eta are obviously one is at 0 and the other is at infinity. So, eta is going to be 0 at y equal to 0 and eta is going to be infinity when y is equal to infinity. So, at these two conditions, I need to find out what would be the values of f or f prime or f double prime. Those would be my conditions. Now, at eta equals 0, what's happening physically? You are at the solid liquid interface. So, your Vx would be 0, and if you look at Vx, what's going to be 0 at eta equals 0? This is going to be 0. If I look at the expression for Vx at eta equal to 0, since my Vx is equal to 0, so f prime, which is df d eta, has to be equal to 0. That is my first condition. Similarly, if I look at infinity, what happens at eta equals infinity in this relation? At eta equals infinity, Vx and u both are going to be equal, Vx equals u. So, my f prime would be equal to 1. Okay. So, that's another boundary condition which I am using. Now, are these two clear to all of you? The next is what happens to Vy at eta equals 0. Using the no slip condition, the x component velocity at y equal to 0, that means on the plate, is 0. But what happens to the x component of velocity? Will it be identically 0 at that point? That is the question that you have to answer. If you are using the no slip condition, if I can say that Vx is 0 at y equal to 0, can I say that Vy is also 0? Vx is 0 on the plate, but can I have Vy non-zero on the plate? No slip means it's no slip in all possible velocity directions. So, on the solid plate, your velocity in the x direction is 0, y and z. Only exception is if you have transpiration or if you have suction on the plate. Suppose the flow is on a membrane surface which has pores and you have pressurized liquid flowing on top of the membrane. So, on the membrane surface there is no x component of velocity, but since you are sucking the liquid out through the pores, your Vy would be non-zero. That's in a case where you have one component 0, the other component may not be 0. Or instead of sucking as in membrane, if you have transpiration, like you are using some flow of air through those pores into the boundary layer, then Vy would be a positive quantity. Okay. So, in transpiration or in suction, you have Vy non-zero, but since the flow in this case is on an impermeable solid, your Vx and Vy are identically 0. The concept of Vx not equal to 0, that is also common in fluid mechanics. Suppose the membrane that I was talking about, suppose it contains a large number of big pores. So, part on y equal to 0, part of the fluid is in contact with a solid, but part of the liquid is not in contact with the solid, it is on the pores. So, at y equal to 0, at some point you have no slip, velocity equal to 0, Vx equal to 0, at other points it is not in contact with solid, so it can have a velocity. So, that is one example of slip velocity, where the velocity at y equal to 0, x velocity at y equal to 0 may not be equal to 0. Okay, that is an example of slip velocity. But for most of the membranes that are used in, let us say, chemical engineering or in biotechnology, they are dense. Okay. So, most of the region is solid, the pores are very small in size. So, for that case Vx is taken equal to 0, but Vy is not taken equal to 0, and Vy would be equal to the suction velocity. So, in our case, since it's more or less an impermeable plate, Vy at y equal to 0 would be 0. And what condition can I put on F if Vy is 0 at eta equals infinity, I mean eta equals 0. This one is 0 at eta equals 0, we have already seen that. So, F will have to be 0 so that Vy is 0. The condition, the three conditions that we are going to use based on our idea of no slip condition and velocity equal to the free stream velocity when y is equal to infinity, that gives me the third condition. There is no slip in the x direction, gives me this condition, no slip in y gives me this condition. So, these are the three boundary conditions which are needed to solve this equation. The development of this equation and the boundary conditions, that should be very clear to all of you. Is there any question? So, now what we are going to do is we are going to take a shortcut. Okay, we are not going to go into the detailed solution of this equation. In 1950s or so, like with a digital computer, someone solved this equation numerically, and we would, the use of the numerical results by someone called Haworth is much better than trying to do the analysis that Blasius has used. So, I am going to give you the numerical result of this equation in a tabular form, and then use those tables to find out the relationship between delta, the relation between the shear stress coefficient, which is exactly like the friction factor for solids, and other necessary or important parameters. So, the numerical results by Haworth. These are some sample results only. Okay. In any advanced fluid mechanics textbook, you would see many numbers in between. I have only copied those numbers which we are going to use in our discussion. So, let us see, using this numerical result, first of all, can we define the edge of the boundary layer? The edge of the boundary layer is the point where the velocity in the x direction is equal to the velocity of the free stream. So, that means small u would be equal to capital U, or in the notation that we are using, Vx would be equal to U. We also know that the gradient of Vx with y would be equal to 0 at y equal to delta. Okay. So, what is the point which corresponds to Vx equals U in this numerical result? F dash equals 0.99155, because by definition, if you remember, we said that the boundary layer thickness or the disturbance thickness is defined where the free stream velocity, where the velocity reaches 99% of the free stream velocity. So, at eta equals 5, the f prime is equals 0.99. So, that means by definition at eta equals 5, you have reached the edge of the boundary layer. So, eta equals 5 is an important number, and that is why I have included the value of eta equals 5 in here. Now, what is the definition of eta? Eta is y root over u by nu x, and this is equal to 5. This is the condition at which we reach the disturbance thickness or the edge of the boundary layer. So, what change you can make in this expression? Would you like to change any of the independent variables in here? I should be able to substitute y by delta, because y is this distance. So, when eta equals 5, looking at f prime, I know that I am at the edge of the boundary layer, whose thickness is defined by, whose thickness is denoted by delta. So, my y becomes equal to delta at eta equals 5. All of you are with me? Any question? Okay. So, my delta is simply going to be 5.0 x by root over r e x. Just a bit of mathematical manipulation, I mean just a bit of rearrangement, and the expression for delta is 5.0 x by root over r e x, where r e x is the Reynolds number, and it is defined as, how do we define dv rho by mu? So, x rho u by mu. So, this Reynolds number, you have seen Reynolds number defined previously in terms of the, let us say, the diameter of the pipe, but the length scale that is used for boundary layer is x rho u, where u is basically u infinity divided by mu. So, depending on where you are on the flat plate, you can have a different value of Reynolds number, and since you have a different value of Reynolds number at each x location, the value of delta would also change. Okay. So, that is the whole idea, that if you change your actual location, your boundary layer thickness at that point will also be different. And if you look at the at this expression, what you would see is whatever we have discussed before. More the velocity, what is going to happen, like you can see what is going to happen if your momentum diffusivity is more, you have a thicker boundary layer, and so on. Now, the next thing that is of importance is what is going to happen to the shear stress at the wall. Okay. Because shear stress at the wall is going to be a function of position, axial position. If you are thinking of finding out what is the friction between the liquid and the solid, you have to find out what is the shear stress at y equal to 0. Okay. Shear stress is between the wall, plate and the liquid. So, what is happening at this point in terms of shear stress? We should like to find that we should like to find out what's its value, and you can see that the velocity gradient, shear stress is proportional to velocity gradient, that we all know for Newtonian fluid. So, that velocity gradient will change depending on where you are in an axial position, because if you are suppose here, then the velocity changes from 0 to v to u infinity within this distance only. Whereas, if you are here, the velocity changes by the same amount over a larger distance. So, obviously, the velocity gradient at this point would be less than the velocity gradient at this point. So, the shear stress is not going to be a constant, rather it would depend on where you are. So, the shear stress that you are going to find out should contain some x in its expression. The same way we have an x for delta. So, shear stress or shear stress coefficient will also have that x in its expression. But as an engineer, you are not interested in finding out what is the shear stress at a specific point. You would like to find out what is the overall shear stress, such that you can multiply it with the area of the plate and find out what force is needed to move the plate in water or in any liquid with certain velocity. So, once you have the expression for shear stress at any point, you have to integrate it over the length of the plate and divide it by the length. So, if you have shear stress which is a function of x, you have to integrate it from 0 to L, where L is the length, and then divide it by L to find out what is the average shear stress, length average shear stress. Once you find that, multiply that with the area, you get the total shear stress. So, never use the expression for tau that you are going to get. Suppose it contains some x, never use what is the value of tau equals L, tau at x equal to L, the value, and then multiply it with area to calculate the total force. Always use the average, length average expression or value of tau, and then multiply it with area to find out what's the force required to move the plate or to keep the plate stationary in a moving fluid. Any question? All right. So, we are going to see what is tau. The wall shear stress denoted by tau W is simply equals mu times del Vx del y at y equal to 0 for a Newtonian fluid. Okay. And this we are simply going to substitute this y in terms of eta, such that we can use the numerical results and so on. So, I'll leave those steps and this is the expression which you would get if you follow the changing the y into eta and so on. I am leaving or changing Vx to psi and psi to f. So, I have skipped a few steps in here which are there in any text. Now, what is the value of d2f d eta square at eta equals 0? If you look at your, this is nothing but f double prime at eta equals 0. If you look at the numerical value which I have given, it's equals 0.332. So, simply you can write tau W is equals 0.332 u rho mu capital U by x So, this is the expression for shear stress for laminar flow over a flat plate, that means 0 pressure gradient flow, and the shear stress at any point can be evaluated using this simple relation. So, now we can appreciate what are the uses of the numerical solution by Haworth, and it's you do not need to have the complete analytical solution, just the numerical solution would be sufficient. The other numbers which I have written on that, like at 8 and 8.4, well, the implications of those would be clarified later on. But tau W, keep in mind it's a function of x. So, if you have to find out the average tau W, integrate it over x over the length of the plate divided by L, then multiply it with area to find out the force. Similar to friction coefficient in solid, something called shear stress coefficient is defined as the shear stress coefficient CF is defined, it is a definition only in this, and it is 0.664 by REX. So, these two, this one and the expression for delta, which we have obtained from the exact solution, exact method by Blasius, these are going to be very useful tool in finding out what is the total amount of force needed, shear stress, and what is the thickness of the boundary layer at each point. Okay. And for that we have used some simple similarity parameter approach. I have shown you how to find out the similarity parameter for a majority of the cases by evaluating the equation at one of the boundaries. The chosen or the preferred boundary would be delta equal when y tends to infinity. Change the equation from PDE to an ODE, solve it numerically, use the results, and these are the two expressions. Now, if you look at tau w, what happens with increase in x? Does the local shear stress increase or decrease? If you move from one axial location to another, Reynolds number increases since you have a larger x. If Reynolds number increases, then tau should decrease. Okay. Reynolds number increases, tau should decrease, and that is consistent with what we have described or discussed before. Over here the gradient is more, the velocity gradient is more compared to the gradient over here, since it changes from 0 to v over a larger distance, gradient less. If gradient less, then shear stress has to be less. So, whenever you encounter such or any formula, see whether or not it is consistent with your understanding, which it is. Any question do you have on up to this point? Okay. So, now what we are going to do in the time that is remaining, I will give you a problem and its, what is the numerical value of its the solution, and we will discuss about the steps. You have to do it on your own. What you have to find out is what's delta star by delta at eta equals 5 and when eta tends to infinity. We know what is delta star, it's a displacement thickness, and delta already known to you, and that's part 1 using the numerical, using Blasius result. And the second thing is so this is a problem which you are going to solve, but before that I would like to discuss something else. The edge of the boundary layer, is it a streamline or not? We know what are stream functions, we know what are streamlines. So, we would like to see if the edge of the boundary layer is a streamline. Now, for that we have to think of some properties of streamline. Now, which property of streamline, what are the properties that you know of? Okay. So, there is no flow across a streamline, and if a particle starts on a streamline, it is going to remain on that streamline throughout its journey. Now, our idea of boundary layer, does it necessitate that there should be flow across the boundary layer edge? There has to be flow across the boundary layer edge, otherwise it cannot grow. So, since you have flow across a boundary layer, that means the edge of the boundary layer is not a streamline. Always keep that in mind, and which you can mathematically prove by showing that Vy is non-zero at the boundary layer edge. You have flow across streamline means your Vy is non-zero. Okay. So, if Vy is non-zero, then there is some amount of liquid coming in or going out, whatever be the case, since it is non-zero. So, streamline, this one is not a streamline. So, I will give you just the basic steps of this problem and you do the rest. We all know that delta star is from 0 to delta 1 minus Vx by u dy. This is the definition of delta star. In order to use the numerical results of Haworth based on Blasius development, you have to convert all the y's to eta, all the v's to psi, and from psi to f. Okay. Once you do that, then you would be able to use the numerical solutions. So, what I would do then is, since I know eta is y u by nu x, so dy would simply be equal to d eta nu x by u. I substitute this in here. So, my delta star simply becomes 0 to some value of eta 1 minus Vx by u. This root over nu x by u would come outside, and instead of dy it is becoming d eta. That's the step which I guess all of you can follow now. So, my delta star would simply be equal to from 0 to eta 1 minus Vx by u. Now, this Vx by u should be expressed in terms of f. So, what is Vx by u? F prime. Okay. So, Vx by u from whatever we have done before is simply f prime. This is e d eta, and what is nu root over nu x by u? Root over nu x by u. Y by eta, nu x by u, can I, if I say it's delta by 5, if you look at the expression for delta, delta is simply 5 divided by that. So, this is simply delta by 5. Okay. So, your delta star by delta is 1 by 5 from 0 to eta 1 minus f prime d eta. Right. So, this is the expression which you would be able to integrate now. It is simply going to be eta minus f within the limit from 0 to eta. So, you can evaluate it at eta equals 5, and you should be able to find out what is eta equals infinity. Now, is it clear? Like your delta, from here what you would get is delta star by delta is 1 by 5 eta minus f 0 to some value of eta. So, this is the expression which you have to calculate for at different eta. So, when eta is 5, it is straightforward. You look at the expression, look at the table, eta equals 5, your f is 3.28 or so. Fine, a numerical value of delta star by delta can easily be obtained, and the value that you should get is 0.34334. This is at eta equals 5. Okay. So, at eta equals 5, find out this, and you get this is the result. But how do you find out eta equals infinity? 8.4 you are saying eta equals infinity. I haven't in the table itself, I haven't given you any eta equals infinity. But why are you saying that at eta equals 8.4? So, if you look at the expression eta minus f eta, and you look at the table, eta minus f eta becomes a constant beyond 8. Okay. So, eta minus f eta, so it is 8 minus 6.27, and eta minus f eta at 8.4, the difference is constant. So, for all practical purpose, we can treat that to be as eta equals infinity. You can find out the value of that as well. So, you would see that the value is about the same, and you have an expression for Vy which is given in your, which we have find out for Blasius case. So, Vy by u, this should be the expression for Vy by u, and once you have Vy by u, then you have to find out the expression, the Vy by u at boundary layer edge. So, if it is at boundary layer edge, that means you have to evaluate it at which value of eta? Eta equals y equals delta, that means at eta equals 5. Because at the edge of the boundary layer, we have seen from before that at the edge of the boundary layer, your f prime is equals 0.99, f prime is Vx by u. So, that happens at eta equals 5. So, if you have to find out what is the ratio of this at the edge of the boundary layer, then eta is equal to 5. Put that over here and you would see that this would be equal to 0.84 by root over Rex. That only shows that Vy is not 0 at y equals delta. So, which says that the boundary layer edge is not a streamline. Okay. So, these are some of the examples of use of Howard's numerical results, and in all the texts that I have given you, you would see more such problems which you should be able to solve. Summarize of what I have taught you today. The basic concept of boundary layer. Why was it important? How did it come into practice? The approximations that one can use in boundary layers, that motion in the x direction is the principal one, but the convection momentum in the x direction predominate over the convection in the y direction. So, del Vx is large, Vy is small, del Vx del x is small, but del Vx del y is large. So, the both terms of the convective part of the momentum transfer in Navier-Stokes, you cannot cancel any with respect to the other. Since convection predominates in the x direction, the diffusive transfer of momentum would be in the y direction. Diffusive transfer in x direction is very small. So, del square Vx del x square would be small compared to del square Vx del y square. So, one term on the right hand side can be neglected, which is the diffusive transport of x momentum in the x direction. So, I will keep the term which is diffusive transport of x momentum in the y direction, and for all boundary layers, when we are going to talk about thermal boundary layer and concentration boundary layer, you would see the form would be exactly the same. Like in hydrodynamic boundary layer, we have Vx del Vx del x. If I change it to thermal boundary layer, it is going to be Vx del T del x. The second term is Vy del Vx del y. If I change it to concentration, the second term would be Vy del C A by del y. When I go to the right hand side, it is mu by rho, which is kinematic viscosity, momentum diffusivity. So, if I have to change it to thermal boundary layer, what should I change? What should I replace momentum diffusivity with? Thermal diffusivity. And the thermal diffusivity, if I remember correctly, it is K by rho Cp. Okay. If I change it to mass transfer, it should be just the mass diffusivity, which is DAB. What is the term in hydrodynamic boundary layer? Del square Vx by del y square. Change it to temperature boundary layer, it will be del square T by del y square. Change it to concentration, del square Ca, which is the concentration of species A by del y square. So, these three equations are fundamentally would be the same, and that would be the starting point for identical or unified treatment of heat, mass and momentum transfer, which we are going to follow next. After that, I said that there can be two approaches for solving these kind of situations. One is an integral approach, the second is a differential approach. We are concentrating on the integral approach for the time being. So, the differential approach. In the differential approach, we have to somehow convert the PDE to ODE, and one way of doing it is combination of variables or finding out a similarity parameter. I have shown you an approximate way to find out how to evaluate the similarity parameter. Once I have the similarity parameter, I simply evaluate Vx and Vy using a stream function, a dimensionless stream function, and all the terms in the equation Vx, del x and so on, I substitute in terms of f, which is a non-dimensional stream function, and eta, which is the combination variable or similarity parameter. I convert the PDE to an ODE, use a numerical solution. The values for different etas, they have some physical significance. For example, I know that at f prime equals 0.99, that has to be the age of the boundary layer. Since my f prime by our definition is Vx by u. So, when Vx is 99% of u, that is the age of the boundary layer. So, I look at the leftmost column, which is eta. So, Vx becomes 0.99 of u at eta equals 5. So, eta equals 5 has to be the age of the boundary layer. The definition of eta contains y. So, if it is at the age of the boundary layer, then y has to be equal to delta. So, I have 5 equals delta times something by x. From that I find out how delta should change with x and other physical properties and process conditions. The next one of importance is what is the total frictional force required or frictional force that has to be overcome for a plate to remain stationary. So, I have to find out what is the shear stress. Shear stress is nothing but mu times velocity gradient evaluated at y equal to 0. Again, I substitute I change everything from v to f and from y to eta, and I see that at y equal to 0, which is eta equal to 0, f double prime has a number given 0.332 or something. So, I have an expression for Cf for tau w, and I see that my tau w agrees with the physical understanding that as x increases, tau decreases since the velocity gradient is less. So, once I have tau w, I also understand that in order to find out the total force, I first have to integrate it over the area. Okay. So, find out the average shear, multiply it with the area, or expression for tau w, integrate it over the area, so that the x dependence has been taken care of. A friction coefficient, exactly like solid friction, Cf, is defined as tau w by half rho u square, where half rho u square is sometimes called the dynamic pressure. Half rho u square, that is it's a definition only, tau w by half rho u square, and we see that the expression that we got is something like 0.664 by root over Rex. So, and then we have used we have seen an example of how to use the numerical results of Haworth for solving some problems, and we have seen that Vy at the age of the boundary layer is not 0, which is true. That means otherwise the boundary layer would not develop. Since you have mass crossing the boundary, that one cannot be a streamline. So, age of the boundary layer is not a streamline. Any question? Thank you.